Hello guys, welcome in ECE 302 Applied Electromagnetic from University of Kufa. In this part we will try to demonstrate an example of electromagnetic plane wave propagation in a Lossy media. This example is 7/4 plane wave in seawater. Of course, this is the textbook fundamentals of applied electromagnetic. Okay, when we need to test plane wave electromagnetic propagation at any material, first we need to test the type of this material, and previously we mentioned how we do that by calculating the ratio this ratio is imaginary or double dash epsilon for a real epsilon, which is equal conductivity to the over angular frequency multiplied by epsilon. So if this is lower than or smaller than 0.01, so we could consider this material as a low losses medium, and if it's larger than 100, so it could be considered good conductor. And definitely if we are talking about lossless or vacuum, so we could depend the rules and the equations for the expressions at lossless medium. So this is just for more simplicity when we solve or when we determine the electromagnetic plane wave electromagnetic propagation through any material. So accept this material loses less or low losses or good conductor, we could consider it as any medium, and we can use the equation for or the rules for any medium. Okay, beside the propagation parameter, the alpha and beta and the intrinsic impedance, we could also calculate the phase velocity and the lambda inside the medium, because we know the electromagnetic wave propagates inside any material with a certain lambda and a certain velocity, okay, which different of the speed at free space, okay, and the wavelength at the free space. So we could use any of this rule according to the type or the behavior of the material. That's good. Let's back to our example. In this example, so we have a uniform plane wave is traveling in seawater. Here the seawater, that's mean we know water with a salt. So assume that the plane wave in xy plane direction, so it will be traveled in that direction, and that's it, okay. And we have travel in positive z direction into the water, it means seawater, and the constitutive parameter of the seawater is the relative permittivity 18, the relative permeability is 1, and the conductivity is 4 Siemens per meter. And here we are informed that the magnetic field at a certain position, specifically z equal to 0, the magnetic is equal the magnetic will oscillate in y direction. So if the magnetic oscillated in y direction and the wave traveled in z direction, that means the electric will be in x direction. So the magnetic at a z or z equals 0 will be 100, this is the amplitude, multiplied by cosine. Of course, this is an instantaneous expression, or what we call real expression of the field. Okay, so we have time here, we have variable of time. 100 multiplied by cosine, the argument of this cosine, 2 pi multiplied by 1000 or 10 to power 3, this is the frequency, multiplied by t, plus 15 degree. Okay, so we need to get expressions for the electric field in instantaneous form, in real or in time domain, or in real expression, and the magnetic. And then we need to determine the depth at which the magnitude of electric field is reached to a 1% of its value at z equal to 0, at this z. So first we need to obtain expressions of electric field and magnetic field. So may someone ask, okay, here we have expression for magnetic, so what's the difference? Why we are asked to determine or to obtain the expression for magnetic field? We get it here. No, this is magnetic field, this is the value of the magnetic field at a certain position. Here we need to find or to obtain or to determine the general expression of the magnetic field and also for the electric field at any position, any z, and at any instant, any t, any time. Okay, so here the magnetic value, okay, or expression at a certain position where z is equal 0. So let's go to the solution. As we said, as long as the H or the magnetic field is directed, or sorry, is oscillated in y direction, and the wave is traveled in positive z direction, so we could expect the electric field will be oscillated in x direction. Okay, let's first write the expression of the electric field and the magnetic field in phase form. So in phase form, the general expression, that means we just will eliminate the t, and we know that the electric field and magnetic field in space domain or in exponential expression, okay, or in, as we said, in phase expression, it's equal to electric field. Here let's start with the electric field, x direction, this is the direction of the oscillation, ex naught, this is the magnitude, we also need to note, multiply by exponential minus alpha z, this is the function of the attenuation, okay, multiply by exponential minus j beta z, and this is the function, the imaginary exponential, which is responsible to the phase. Of course, both of them, okay, give us exponential minus gamma multiplied by z, and this gamma is equal to alpha plus j beta. Okay, we just decompose this gamma or the propagation constant to this two exponential function, but please note the first exponential function is real and it's responsible to the attenuation and its effect on the magnitude, just on the magnitude. Okay, and the second one, it's imaginary exponential and responsible to the phase, okay, and the sinusoidal. This exponential give us the sinusoidal. Okay, and definitely the magnetic field is equal to the electric field divided by the intrinsic impedance, and it's oscillated in y direction, as equal to the Ex naught, the magnitude of the electric field, divided by the complex intrinsic impedance. Now we don't have, or we still don't specify the type of the material. Okay, multiply by the attenuation exponential, multiply by the phase exponential. So we could now, this is the general expression for electric field and the general expression for the magnetic field, and if we need to convert them or rewrite them to be in time domain, so we need to multiply by exponential minus j omega t. Sorry if writing is so bad. Minus, okay, and then take the real part for the all expression. Before we do that, we need to know this value, okay, the unknown value. For example, the Ex naught, we need to know how much this, the amplitude, and we need to know alpha, and we need to know beta, and we need to know the intrinsic impedance, okay, to specify or to write the complete expression for the electric field and magnetic field at any z at any t, general one. So to determine alpha, beta, and intrinsic impedance, first we need, or as we said, it's prefer to specify the type of this material or the behavior of this material, okay, for more simplicity. So first we will go to calculate the ratio double dash to dash, or omega to sigma to omega multiplied by conductivity over angular frequency multiplied by permittivity. This is to specify the type of the material, and here we get 9 multiplied by 10 to the power 5. Oh, it's so large, it's larger than 100, so it could be considered good conductor, okay. Seawater, okay, at this value of conductivity and this value of omega and permittivity behaves as a good conductor, so we could use the rules or the expressions in good conductor to calculate alpha, and if we could get alpha, it's equal to beta, and then we could calculate intrinsic impedance. So here alpha is calculated. We know f, the frequency, of course, because we could we could expect it from the expression of the magnetic field here, from the given expression here. We could expect it f, which is equal 1000 hertz, 10 to the power 3. So from this we could expect it the frequency f. So by using the rules of the expressions for alpha and beta intrinsic impedance for good conductor, we could calculate alpha is equal under square root 5 times 1000 f times permeability 1. Permeability is equal to the permeability of the vacuum, all the material which have non-magnetic properties, its permeability is equal to the permeability of the vacuum, okay. It's equal to the permeability of the vacuum. Why will permeability is equal to the mu naught. So alpha is equal to 0.126 ampere meter, and because in good conductor alpha is equal to beta, so beta is equal 0.126 rad per meter, and the intrinsic impedance also it could be calculated and it could be expressed as a phase, magnitude and phase. So we could write the intrinsic impedance as a magnitude and phase to be 0.041, 0.044 exponential j pi over 4. This is the magnitude and phase for the intrinsic impedance. Now we get alpha and beta and intrinsic impedance. That's good. So let's start to try to write the expression of the electric field and then the expression of the magnetic field. Of course, in instantaneous expression, that's mean with time. And as we said, if we need to write it with time, we need to multiply by exponential j omega t, okay, and then all this expression, take the real part for all this expression. Also, we need to multiply it here with exponential j phi naught, and we said that this the initial value because we don't have any information about the initial phase of this expression, so we need to find them. So here we have magnitude, of course, the oscillated direction, magnitude of ex naught, exponential j phi, this is the initial, we need to add it, we need to be informed about it, and exponential of the attenuation, and the initial of the phase, and here the initial of the phase by the time, and the initial of the phase by the z, and the initial of the exponential of the phase by the time plus the exponential or multiply by the exponential of the phase by the space z, and exponential of the initial phase. Okay, all of them represent the argument of the sinusoid, and real exponential which represent the initial of the attenuation, okay, which affect on the magnitude. So the real part all of this will equal, of course, out of the cosine we will have the magnitude multiplied by the exponential of the attenuation. The exponential of the attenuation, we get alpha, it's equal 0.126 multiplied by z. Then cosine 2 pi times f, this is the omega, this is omega t, 2 pi times f omega multiplied by t, this is from the first exponential, minus beta multiplied by z, this is beta multiplied by z, of course minus here because we have minus j, plus the initial phase from the first exponential. So again, initial phase from the initial phase exponential, minus beta z, this is minus beta z argument, okay, and omega t, this is 2 pi f, it's omega multiplied by t. So all of this is the phase, the argument of the cosine, we call all this is the phase of the wave of the field. Same thing for the magnetic, we just have the magnitude of the electric field divided by the intrinsic impedance. In intrinsic impedance we also have magnitude and phase, because the intrinsic impedance represents the relation between the electric field to the magnetic field. So this relation, it could be real if there is no any delay between the oscillating of the electric field and the oscillating on the magnetic field, and this is happening just in free space, okay, in free space, where is the free space here, okay, or in very low losses, but otherwise this This should be complex. That means the protection or the oscillation of the magnetic field may be lag or lead from the oscillation or the protection of the magnetic electric field. That means there is a time delay between the oscillation of both of them. Maybe the electric field lead and the magnetic field lag. Okay, so this delay represented by phase in mathematics. Okay, and this phase here it's equal to pi over 4. Okay, this pi over 4, which is angle in radian, represent delay in real world between electric field and magnetic field. So this exponential is raised here and be minus j by 4. Okay, just rise and be minus. So here we have extra phases in magnetic, omega t from the omega t, beta z from beta z. Okay, the attenuation, this is out of the cosine, and the initial phase minus 45 degree. The 45 is pi over 4. Okay, this is resulted from the phase between the magnetic field and the electric field. This is the phase difference between the magnetic field and the electric field. So the magnetic field will be the key because we already have information about the magnetic field where at z equals to 0. At z equal to 0, we know the magnetic field is equal this expression. Is equal, sorry, the previous expression. Okay, so we could equal the given expression in the questions with this expression at z equal to 0. So at z equal to 0, this expression will equal 22.5. This is from this production multiplied by ex naught, the magnitude. This is still unknown. Multiplied by cosine 2 pi times frequency. We know this. There is no beta z here because we already z is equal to 0, plus initial phase minus 45 degree. So by compare this with this is given in the question. Okay, we could find here first the magnitude, because now we, by comparison, we could equalize this with this. So 22.5 multiplied by ex naught is equal to 100. Here we have ampere per meter, here we have milliampere per meter, so we need to equalize the units. So the 100 multiply, we need to convert it to the ampere, milliampere converted to the ampere, so we need to multiply by 10 to minus 3. So according to that, we get magnitude, initial magnitude, maximum magnitude of the electric field is equal to the 4.44. And also we could equalize the summation of these phases with the 15 degree here. Okay, so according to that, the initial phase is 16 or 60 degree. So now we have everything. We could write the electric field expression in time domain, the general one, and the magnetic general one. Okay, here we have omega t, beta z, plus the initial phase. Here we have omega t, beta z, and the initial phase minus the 45 from the intrinsic impedance. So 60 minus 45 is equal to the 50 degree. So I think we have other thing to do. Okay, so in branch B we need to calculate the magnitude of electric field, okay, or the depth where the electric field is equal to 0.1% or 0.01. Okay, the depth at which the amplitude of electric field decrease to 0.01 or 100% of the initial at z equal to 0. So at z equal to 0 here, if we just go back to the general expression, okay, and substitute z equal to 0, if z equal to 0 here, we get 1, okay, exponential, and according to that, so it's 4.44 at z equal to 0. Let's see what he did here. So obtain from 0.01, this is the 100.01. okay, yeah, that's it. Okay, so here we need to calculate the depth at which the amplitude of the electric field decreased to 1% of its initial. So that means we need to calculate where the 0.01, this is the 1%, multiply by the maximum AX naught, it's equal to EX naught for the amplitude multiply by exponential minus alpha z. So this is cancelled with this and we get 0.01 is equal to exponential minus alpha plus z. Definitely we take ln to the both side and then find z, and z here it's equal to about 36 meter or 37 meter. Okay, we just equalize the magnitude of the electric field multiplied by exponential minus alpha of z equalized by 100% of the magnitude of the electric field. So this magnitude with this magnitude 100% equal to this, and take the ln for both sides and then find z. That's it. Okay.